Hey everyone, welcome back to The Explainer. So if you've been hanging out with us for this series, huge congratulations. We've officially conquered part 1 on physical properties, part 2 on the chemical properties of metals, and part 3 where we dove into nonmetals and ionic compounds. Today, we are wrapping up Class 10 Science, Chapter 3. We're going to uncover the complete kind of hidden life cycle of metals, literally from how we pull them out of the dirt to how they eventually break down over time.
But before we get into the weeds, have you ever actually just stopped and wondered, where do metals come from? I mean, think about it. When you buy an iron rod or copper wire or even a shiny gold ring, you're getting a perfectly purified product. But there's no underground factory where you can just dig a hole and pull out a perfectly formed shiny iron rod. No way. Out in nature, metals are absolutely not found in that pristine form. We really have to work for them.
So here's our game plan for today. We'll start with nature's hidden metals, then walk through the extraction process, see how reactivity dictates the method, look at the threat of corrosion, and finally, preventing rust and decay. All right, Section 1, Nature's Hidden Metals, focusing on minerals and ores.
So metals occur naturally right beneath our feet in the Earth's crust, but they're almost always chemically glued together with other elements, like oxygen, sulfur, or carbon. We call these naturally occurring mixed-up substances minerals. You're rarely just going to trip over a pure chunk of metal out in the wild. Instead, they're trapped inside these rocky compounds mixed with a bunch of impurities. We give these rocks specific names, things like bauxite, hematite, galena, or zinc blende. But really, at the end of the day, they are just rocks holding metals hostage.
Now, we really need to clear something up. The difference between a mineral and an ore. So while all minerals contain metals and impurities, an ore is a very specific type of mineral. It's one where we can extract the metal economically and conveniently. Think about it. If a giant rock only has like microscopic traces of iron in it, spending millions of dollars to dig it up, crush it, and process it, yeah, that wouldn't make any financial sense at all.
Which brings us to a really famous chemistry phrase you gotta remember. All ores are minerals, but all minerals are not ores. It sounds a little bit like a riddle at first, but honestly, it makes total logical sense. We only bother extracting metal from the specific rocks, the ores, that actually have a high enough concentration of metal to make the whole crazy factory process worthwhile. We're not just trying to squeeze metal out of every random stone we find.
Just to give you some concrete examples, if we need iron to build steel beams, we go hunting for its specific ore, hematite. If we want aluminum for, say, airplanes or soda cans, we mine bauxite, which is packed with aluminum oxide. And for zinc, we look for zinc blende. Putting actual names to these sources kind of helps us realize that before metal becomes a shiny tool, it starts its life as a very carefully chosen rock.
Moving right along to Section 2, the extraction process. How we actually go from a rock to metal.
Getting that pure metal out of its rocky prison generally happens in 3 main stages. Stage 1 is the concentration of the ore. Stage 2 is converting that ore into a metal oxide. And the third and final stage is reduction to pure metal. Let's break these down so you can see just how brilliant this whole operation really is.
Okay, stage 1. This is all about dealing with the gangue. And gangue is just a fancy word for all the unwanted garbage. Sand, clay, mud, useless rocks that we accidentally dig up along with our valuable ore. It's kind of like making loose-leaf tea. You wouldn't just throw twigs, dust, and stones into your mug, right? You filter the bad stuff out. So concentration, which is also called enrichment of the ore, is exactly that. It's a cleaning process to get rid of the gangue so we're left with a much purer metal compound. Once we've cleaned it up, we hit stage 2, converting it into a metal oxide. Now, the method here depends on the ore. If we have a sulfide ore, we use a process called roasting, which literally means heating it intensely with lots of oxygen around. But if our ore is a carbonate, we use calcination, which means heating it up strongly but without air. The whole point of both of these? To leave us with a metal oxide. Because, trust me, oxides are way easier to handle in the next step.
And that brings us to the grand finale, stage 3, reduction. We have our metal oxide, but we just want the pure metal. So we bring in carbon. Carbon acts as our reducing agent. We throw the metal oxide and the carbon into a massive furnace and crank up the heat. Because carbon is super reactive, it basically swoops in, steals the oxygen atoms right off the metal, and boom, leaves our pure, uncombined metal sitting right there, ready to be poured.
All right, Section 3, reactivity dictates the method.
Here's the catch though. Not all metals act the same.
They have wildly different chemical personalities, which totally changes how we extract them. That carbon trick we just talked about doesn't work for everything. Take the highly reactive metals at the top: potassium, sodium, calcium, magnesium. They hold on to their bonds so tightly that carbon can't break them. We literally have to zap them with intense electricity in a process called electrolysis. Then, in the middle, your moderately reactive metals like zinc, iron, and lead, those can be extracted using the standard carbon reduction. And at the very bottom, the least reactive metals like gold, silver, and platinum. They are so chilled they barely react with anything, so nature basically leaves them alone, meaning you can often find them just sitting in the ground in their free, pure state.
Next up, Section 4, the threat of corrosion, or as I like to call it, the enemy of metals.
So, have you ever noticed that bright orange rust flaking off an old iron gate? Or maybe that weird, dull brown coating on some forgotten tools in the garden? Well, that is corrosion in action. It's the slow, relentless destruction of metals caused by chemical reactions with air, moisture, or other chemicals. It is literally just nature trying its absolute hardest to turn our nice, refined metal back into a useless, rocky mineral.
Now, for rusting, which is definitely the most famous type of corrosion, iron needs two specific things to be present at the exact same time: oxygen and water. That includes moisture in the air. If you only have oxygen, but the air is bone dry, no rust. If you submerge iron in pure water that has absolutely zero oxygen in it, still no rust. It's that combination of the two working together that completely spells disaster for iron.
And I really want to stress the stakes here are huge. Corrosion is not just some ugly cosmetic issue. It fundamentally weakens giant support structures, it damages vehicles, making them totally unsafe, it destroys underground pipelines, which causes massive leaks, and honestly, it creates a massive economic loss. Every single year, billions of dollars are spent globally just repairing or replacing metals that have basically surrendered to corrosion.
Which leads us to Section 5, preventing rust and decay.
Because corrosion is such a huge problem, we've had to invent an entire arsenal of defense mechanisms. The easiest one is just painting the metal, which literally puts a physical wall between the iron and the wet air. Oiling and greasing do the exact same thing, which is super useful for moving parts like your bike chain. But my favorite method is galvanization. This is where we take iron and coat it in a thin layer of zinc. Since zinc is actually more reactive than iron, the zinc essentially sacrifices itself. It takes the hit from the environment, creating a shield that keeps the iron underneath perfectly safe. It's absolute chemical genius.
Another super clever trick is alloying. Instead of using a pure metal, we melt it down and mix it with other metals, or even non-metals, to create an alloy. This completely upgrades its properties, making it way stronger and incredibly resistant to rust. I mean, look around your house. Brass musical instruments, that's an alloy of copper and zinc. Beautiful bronze statues are copper and tin. And that shiny stainless steel in your kitchen, that is a genius mix of iron, chromium, and nickel that stops your forks and spoons from ever rusting in the sink.
So what's the big takeaway here? Why does all of this actually matter? Well, because understanding extraction and corrosion isn't just some boring textbook theory. It's the absolute foundation of our modern world. It's the very science that lets us produce pure metals, build towering skyscrapers, manufacture the cars we drive, and ultimately save incredible amounts of resources and money by keeping those metals from rotting away.
Wow, we have covered a massive journey today. From a dirty, rocky ore hidden deep underground, through the crazy intense heat of a blast furnace, all the way to that gleaming stainless steel spoon in your kitchen. So now that you know the hidden life cycle of metals, how are you going to look at the world built around you? Next time you cross a steel bridge or even just pick up a coin, I hope you remember the incredible science it took to get it there and the constant battle to keep it from turning back to dust. Thanks so much for hanging out with us for this explainer. Keep observing and keep questioning.